This is Math 432, Applied Combinatorics, and I'm Professor Azaf. The problem that is going to permeate the next few videos is going to be the art gallery problem. It can be stated like this. How many guards are needed for an art gallery if each guard, suppose here's a guard, has a 360-degree view, so suppose each guard can swivel around in a spot but can't move, and you want every wall of the museum to be visible to a guard. So we can think about building a museum. A museum's got a bunch of walls, and you don't want to think of rectangular rooms. We want to think of Frank Gehry designing the museum or something. So we're going to allow for odd things like this. Okay, well, in this case, one guard's enough. And in fact, whenever we have something that's convex, one guard is enough. This guard, if she swivels her head around, can see every wall. So that's one case that we have. So in the case that we have a convex polygon that is the shape of the room, so convex means that, well, there are different ways to define it, but the angles are never more than 180 degrees. Another way to say it is that if I connect any two points on the boundary, the line connecting them goes in the interior and doesn't leave it. So here, for this case, the answer is 1. Only one guard is needed. But we could have a more exotic shape. So again, we could kind of angle things in like this. It's like, okay, well, she can still see everything, but actually if we kind of bring the walls in a little bit, and let's give her a little bit more excitement here. So let's make these kind of comb-shaped pieces, where we're going to have like these little exhibits, where maybe you're going to go in here and see Picasso's Cubist period, and then over here you can see some of his Renaissance style art that he did. Okay, and now we have this is your shape. So let's make this your art museum. The question is, how many guards would you need for this? Well, I can push this out. So here, if we put one guard in here, she can't see into here. She can't see on this wall. So one guard's not enough. And in fact, if you think about this shape for a second, you'll see that actually we're going to need one guard to go in each of these cubbies. And so we have a guard in here, a guard in here, so they can swivel around, remember, so guard in here. And then this guard, if we put her out here, then she can see down the hall and inside the cubby. So this is what we'll call a pathological case. In this case, what we have, I guess I can draw it like this. So we're going to have a museum that has these combs coming out of these sort of spiky regions. And then in this case, we can think about, well, how many walls does this museum have? So we're going to need one guard here, a second guard here, a third guard here, and a fourth guard here. And as long as we put one of those 4 guards sort of to look down the hall and not just inside the little spikes, we'll be fine. So in this case, we need M guards if we have M spikes for M spikes. And then in this case, we have 3M walls. So we can think about counting up the walls, and then you can see if I sort of think about these flat regions and these combs, I have 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So I can think about this as having, okay, a total of 3M walls, and I actually need 3 guards in this case. So we can ask ourselves, is this the worst case that we need? Will we always be able to do it if we have M walls? The number of walls in a polygon is the same as the number of edges, right? Which is also going to be the same as the number of vertices, even when you make it kind of go in like this. So this is telling us something about the number of vertices and the number of guards that's needed. And the question is this the worst case? Can we always do it with at most this many guards? So we know that we can sometimes do it with fewer, right? No matter how many edges you put on this convex polygon, we only need one guard. But in the worst case, is this really the worst case? And that's what the art gallery theorem is trying to get at. So the theorem says that yes, this is the worst case and this is enough. So we can state the art gallery theorem in a museum with N walls, N over 3, and now you have to think, well, that might not be an integer, right? But we'll take the floor of it. That'll be an integer. So that's you take N over 3, and then you just remove the decimal part. n/3 guards suffice. Now, it says suffices. We can sometimes do it with fewer, but the point is that we want to prove that we don't need more. So we know that that's the most number of guards that we have to have, but we also want to know not just how many guards do we need, but how should we place them. In this example, we needed to place one in each spike region and then one over here, but in general, when we're having a problem like this, having an abstract solution, well, this is how many guards, is good, but it'd be better if we can know where the guards are placed. And this is going to be one of those proofs that'll tell us not only that the result is true, but how to do it. So in the next few videos, we're going to be proving this theorem, and we're going to have to prove a few lemmas along the way, statements about polygons that are going to help us prove the famous art gallery theorem.